off when you're not. Committee on Science, Space, and Technology will come to order. Without objection, the Chair is authorized to declare recesses of the committee at any time. Welcome to today's hearing entitled Exploration of the Solar System, from Mercury to Pluto and Beyond. I'll recognize myself for an opening statement and then the ranking member. The exploration of our universe captures Americans' interest, inspires us to pursue extraordinary goals, and keeps us on the forefront of scientific achievement. It also is what NASA was created to do. Since 1958, NASA has led the world in space exploration with a long list of firsts. NASA built, launched, and operated the first spacecraft to encounter another planet, the first spacecraft to leave our solar system, and the first spacecraft to take humans to the moon. Earlier this month, a New Horizons spacecraft achieved another American first by being the first spacecraft to reach Pluto. The photos and data sent back to Earth continue to capture the imagination of people around the world. These pictures show mountains of water ice, caverns deeper than the Grand Canyon, and evidence of geologic activity. And while we may not resolve debates about Pluto's planetary status today, at least one thing is for certain: Pluto has a heart. And this is just the beginning. It will take up to 16 months for all of the data from the Pluto system flyby to be downloaded. NASA, the Southwest Research Institute, the Applied Physics Laboratory, and the New Horizons team deserve our appreciation for the successful mission to Pluto. NASA also has ongoing missions to explore Mars, Jupiter, Saturn, and the asteroid belt. The Dawn mission to Ceres and Vesta continues to transmit impressive images and important science. Juno is on its way to Jupiter, scheduled to arrive next year, and pave the way for a future mission to Europa. These missions are the result of investments made a decade ago or longer. It is crucial that NASA continue to explore our solar system. Planetary science teaches us about how our solar system works and provides clues about how it was formed. Planetary missions discover the locations of minerals and potential water sources on asteroids, comets, moons, and planets that could be used on human missions or extracted for use here on Earth. Space exploration also inspires the next generation of young people to pursue careers in science, technology, engineering, and math. Today, young students across the country are reading about New Horizons, looking at photographs of Pluto, and are excited about one day exploring the cosmos themselves and making new discoveries. Unfortunately, the Obama administration's past and present proposed cuts to planetary science and exploration at NASA have made it clear these endeavors are not its priority. The administration's fiscal year 2016 request cut funding for planetary science by $77 million from fiscal year 2015 levels. Our committee's NASA Authorization Act for fiscal year 16 and 17 restores these crucial funds to the science and exploration accounts. Funding levels requested by the Obama administration would slow the rate at which we can develop, build, and launch new missions like New Horizons. This committee's bill and the funding levels approved in the House would allow NASA to keep planetary missions like New Horizons on track. So I urge the administration to support this common sense, balanced, and reasonable approach, which will keep us on the forefront of space exploration and discovery. I do thank our witnesses for being here today. We look forward to their testimony in just a minute, and I'm going to yield the balance of my time to the gentleman from Texas, the chairman of the Space Subcommittee, Bruce Babin.
Thank you, Mr. Chairman. Space exploration is a challenging endeavor that distinguishes the United States as a global leader, supports innovation and economic growth, and inspires the next generation to build, explore, and to discover. The success of the Dawn mission to the asteroid Ceres and the New Horizons mission to Pluto demonstrate the national importance of space exploration and planetary science. Unfortunately, year after year, the Obama administration has consistently cut funding and deprioritized NASA space exploration and planetary science. It is imperative that Congress continue to reject the administration's cuts and support a well-funded exploration program. My congratulations to Dr. Stern, NASA, and the New Horizons team on a successful mission to Pluto, and I thank all of the witnesses for being here today and look forward to their testimony. I yield back the balance of my time.
Thank you, Mr. Babin. The gentlewoman from Maryland, Ms. Edwards, the ranking member today, is recognized for her opening statement.
Thank you very much, Mr. Chairman, and thank you to the witnesses. Good morning, and I appreciate being able to sit here on behalf of our ranking member, Congresswoman Eddie Bernice Johnson, who's on travel out of the country today with the President. I want to join the Chairman in welcoming our witnesses in today's hearing, and we have such a distinguished panel, so I truly do look forward to your testimony. I believe we live in rather extraordinary times. We could see from the successful flyby of Pluto just 2 weeks ago and the announcement last week that an Earth-like planet had been discovered in the habitable zone of another star's solar system are just the most recent examples of the tremendous accomplishments that have been made in planetary science and space exploration in recent years. And it's quite notable that all of the solar system exploration missions that NASA has undertaken over the past half-century have raised as many exciting new research questions as they've answered. That is the nature of space exploration, and it's why it's so important for this nation to continue to support it. The New Horizons mission to Pluto is also a reminder of how challenging solar system missions really are. The 9-year flight to Pluto was preceded by years of design and engineering work to produce the spacecraft and instruments and the trajectory that made New Horizons a success. I do want to salute the entire New Horizons team for their dedication and hard work over these many years. And I'm sure that Dr. Stern will have much more to say about the work that went into making the mission a success. But I also want to acknowledge and take note of the significant role played by Dr. Tom Cremegis and the Maryland-based Johns Hopkins Applied Physics Laboratory. You can tell we're very proud of APL in the development and execution of the New Horizons spacecraft and mission. They and the entire Pluto mission team can take pride in what has been accomplished. Mr. Chairman, the nation is making great progress in the exploration of our solar system. However, that progress has been made possible in large part by the investments in technology development that our predecessors had the foresight to fund. Frankly, it's now our turn as members of Congress to show the same vision, and I hope we will, by the time this year's funding battles get resolved, show that kind of commitment. We owe it to the dedicated scientists and engineers represented here today to do that. Yet progress in solar system exploration is not just a question of funding. Those funds will need to be invested judiciously to ensure that NASA has the right technological capabilities in the years ahead. In addition, there will need to be clear and thoughtful prioritization of research objectives, because there really is an embarrassment of riches when it comes to exciting new potential mission concepts. That's where the decadal surveys of the national academies can continue to play a very useful role. As members of Congress, we all may have our own favorite destinations and missions, but it's important that the scientific community be at the forefront to determine priorities that address the most compelling scientific questions while ensuring that the planetary science program remains an appropriate balance across research fields. In the meantime, today's hearing is a wonderful opportunity to hear about some of the exciting results from missions now underway, as well as those being contemplated. And I truly cannot wait to hear from our witnesses. And I would say, just in closing, a reminder to us that this work, as you all have described, is difficult, it's complex, and the last thing that you need are members of Congress meddling in the scientific work. And so I look forward to hearing from you about what is going on now and what the prospects are, and I would like us as members of Congress to step aside, make sure that we provide you the resources that you need, and expect that we may not know the value of that for 50 years in the running, and I am indeed okay with that. Thank you, and I yield.
Thank you, Ms. Edwards, and let me introduce our panel today. Our first witness is Dr. John Grunsfeld, Associate Administrator for the Science Mission Directorate at NASA. Prior to his appointment as administrator, Dr. Grunsfeld was Deputy Director of the Space Telescope Science Institute, where he managed science programs for the Hubble Space Telescope and James Webb Space Telescope as well. Dr. Grunsfeld also has served as NASA Chief Scientist, Chief of the Computer Support Branch in NASA's Astronaut Office, and Chief of the Extravehicular Activity Branch. Dr. Grunsfeld has flown aboard 5 Space Shuttle flights, including the Atlantis, Discovery, and Columbia, logging over 58 days in space and more than 58 hours of spacewalk time. He is a recipient of many awards, including the NASA Constellation Award. Dr. Grunsfeld earned his Bachelor of Science degree in Physics from MIT, his Master's of Science degree in Physics from the University of Chicago, and his PhD in Physics from the University of Chicago. Dr. Alan Stern, our next witness, is the principal investigator for the New Horizons mission at the Southwest Research Institute, which has a facility in my hometown, San Antonio, Texas, and in Boulder, Colorado. Before working at the Institute, Dr. Stern was Associate Administrator for the Science Mission Directorate at NASA. He also served on the Board of Directors of the Challenger Center for Space Science Education and was Director of the Florida Space Institute and Chief Scientist and Mission Architect for Moon Express. Among other accomplishments, Dr. Stern has been awarded the von Braun Aerospace Achievement Award of the National Space Society and Smithsonian Magazine's American Ingenuity Award. Dr. Stern holds 2 bachelor's degrees in physics and astronomy and Master of Science degrees in planetary atmospheres and aerospace engineering from the University of Texas at Austin. He has a PhD in astrophysics and planetary science from the University of Colorado at Boulder. Our third witness today is Dr. Christopher Russell, Principal Investigator for the Dawn mission and Professor of Geophysics and Planetary Physics at the University of California, Los Angeles. Dr. Russell is also Principal Investigator of the Magnetic Fields Investigation on the Magnetospheric Multiscale Mission and Lead Investigator for the Magnetometer for the InSight Mars lander. Dr. Russell has received the American Geophysical Union's McIlwain and Fleming Medals and COSPAR's Science Award, and even has an asteroid named after him, asteroid 21459, Chris Russell. At least I am jealous of that. You too? Dr. Russell earned his Bachelor of Science degree from the University of Toronto and his PhD from the University of California, Los Angeles. He has published over 1,500 scientific papers, receiving over 44,000 citations. Our next witness, Dr. Robert Papalardo, is a study scientist for the Europa mission concept at NASA's Jet Propulsion Laboratory. He has previously served as the project scientist for the Cassini Equinox mission at Saturn and as study scientist for Jupiter Europa Orbiter. Prior to working for NASA, he was an assistant professor of planetary sciences in the Astrophysical and Planetary Sciences Department at the University of Colorado at Boulder. He also was an affiliate member of the Galileo imaging team, where he worked to plan many observations of Jupiter's icy satellites. He is a recipient of honors including NASA's Exceptional Service Medal, the NASA Group Achievement Award, and the JPL Mariner Award. He received his Bachelor of Arts in Geological Sciences from Cornell University and his PhD in Geology from Arizona State University. Our final witness today is Dr. Robert Braun, David Andrew Lice Professor of Space Technology at the Georgia Institute of Technology. Dr. Braun is also the founding director of the Georgia Tech Center for Space Technology and Research. Dr. Braun has served as NASA Chief Technologist. He also has served as a member of the Mars Pathfinder Design and Landing Operations Team and as part of the development teams for the Mars Microprobe, Mars Sample Return, and Mars Surveyor 2001 projects. He is the editor-in-chief of the AIAA Journal of Spacecraft and Rockets and is the author or co-author of over 275 technical publications. He is a recipient of many awards, including the 1999 AIAA Lawrence Sperry Award and 2 NASA Exceptional Achievement Medals. Dr. Braun received his bachelor's degree in aerospace engineering from Penn State, his master's degree in aeronautics from George Washington University, and his PhD in aeronautics and astronautics from Stanford. As the members can see, this is an exceptionally qualified panel of experts. They have wonderful backgrounds, wonderful expertise in all kinds of areas. We welcome you all today. And Dr. Grunsfeld, will begin with you.
Well, thank you very much for the opportunity to appear today. And I want to say right off the bat that you are all team members in this great enterprise. For over the last 50 years, we have been on an epic journey of discovery, true exploration, and the results have been extraordinary. 2 weeks ago, NASA's New Horizons spacecraft made a historic flyby through the Pluto system. This capstone event celebrates the fact that in the last 50 years, the U.S. has been the first to visit each of the planets and now the dwarf planet Pluto in our solar system. Our NASA Planetary Science program leads the world in the exploration of the solar system, and I'd like to take you on a short journey through that solar system. This is an image. Many of us forget that the sun is the center of our solar system from yesterday from our Solar Dynamics Observatory. Mercury from the Messenger spacecraft. We discovered a new world through the Messenger mission. Venus from the Magellan spacecraft. 1990, launched from the Space Shuttle. The Earth. The Earth is, in fact, a planet from our new Discover mission, 1,000,000 miles from Earth. Mars, I had to get a Hubble Space Telescope picture in there, taken from the Hubble. Ceres, in the main asteroid belt, the largest dwarf planet in the asteroid belt, from the Dawn mission. You'll hear about that. Jupiter, from Galileo, arrived 1995, also launched from the Space Shuttle. Saturn, from Cassini, still exploring. Uranus, from Voyager 2. Neptune, from Voyager 2. And the capstone, Pluto, as we've just seen from the New Horizons, July 14th. And as you can see from this last image, Pluto has not disappointed the scientific community or the public. In April, the NASA Messenger mission hit the surface of Mercury as planned after a stellar 4-year mission. A key science finding of the mission is compelling evidence that Mercury harbors water ice and other volatile materials in its permanently shadowed craters. On Mars, we have the Curiosity rover. It's already shown us that Mars is a highly evolved, dynamic planet that once could have supported microbial life and has the potential to support human life in the future. Future missions to Mars include the InSight mission, which will launch in 2016, providing our first look into the deep interior of Mars, and the NASA Mars 2020 rover, which will be the first to acquire geologic samples for potential future return. The Dawn mission, as you'll hear, is currently studying the dwarf planet Ceres, which is the largest object in the main asteroid belt. Dawn has the distinction of being the first spacecraft to orbit a dwarf planet. Asteroids and other small bodies continue to be objects of importance for NASA to study, and we're currently developing a very ambitious mission for a robotic asteroid rendezvous and sample return dubbed OSIRIS-REx, which is planned to launch next year. On the way to Jupiter, as you've heard, is our Juno mission, which will arrive next year. The biggest planet in our solar system. The mission will investigate our largest planet's composition, atmosphere, belts, and magnetic field. Jupiter is host to a collection of amazing moons, several of which are larger than our own moon. Europa, which you'll hear about, may harbor a salty ocean underneath a thick crust of ice with the potential to harbor life. NASA is working on a mission that will send a highly capable spacecraft to investigate this fascinating world. At Saturn, Cassini spacecraft recently observed the moon Enceladus, emitting sheets of water or plumes from features on the surface. These plumes may come from subsurface lakes that could represent safe harbors for microbial life. In 2017, the Cassini mission will be sent on a brand new mission. As it runs out of fuel, it will orbit Saturn and then enter the Saturnian atmosphere, a dramatic and fitting end for a transformative planetary explorer. While we have no current plans to visit Uranus and Neptune, the James Webb Space Telescope, which will launch in October 2018, promises to provide extraordinary science by observing these giant icy planets in unparalleled spectroscopic detail. And still further out, Voyager 1 and 2 continue to operate as part of Voyager's interstellar mission. The two Voyagers hold records as the longest operating and the most distant spacecraft ever built by humankind. The United States has been the first nation to successfully reach every planet, from Mercury to Pluto, with a space probe. But our study of the solar system does not stop at Voyagers or New Horizons. We continue to seek fundamental science questions, including whether we are alone in the universe. NASA will probe deeper into this question by studying solar systems around other stars, exoplanets, using Hubble, Spitzer, Kepler, and launching in 2017 the Transiting Exoplanet Survey satellite. This great journey into the unknown continues, and there's still much to be learned. With your support, our future missions will advance along this path of exploration, discovery, and innovation for generations to come. Thank you.
Thank you, Dr. Grunsfeld and Dr. Stern.
Well, thank you very much. Thank you for the opportunity for New Horizons to appear today to discuss NASA's exploration of the Pluto system. I'd like to start, if I may, by introducing Glenn Fountain, who's our project manager, and several members of our team who came downtown. If they would stand up, I would appreciate it. 2,500 Americans work to make us all proud, and they are representatives of that team. Well, if I can have the first time step in the view graphs. Next one, there you go. There's a picture of our spacecraft and a cartoon drawing both on the left, and of course our launch on an Atlas V back in 2006. I want to say just a little bit about this spacecraft. It only weighs about 1,000 pounds. It is an amazing testament to the technology developed in NASA. We didn't send two of these like in the grand days of Mariner and Pioneer and Voyager. One lone spacecraft across 3 billion miles of space. It carries 7 scientific instruments so sophisticated that all 7 combined weigh less than just the camera on the Cassini-Saturn orbiter. All 7 together, when all operating, draw 28 watts, less than half a light bulb, and yet they represent thousands of times the power of the instrumentation built in the 1970s for Voyager. If I can have the next time step, this is the epic journey that we just completed. We launched from Florida in January of 2006, the fastest spacecraft ever launched, 9 hours to the orbit of the moon, about 10 times faster than Apollo, only 13 months to reach Jupiter. Compare that to 6.5 years for Galileo, 4.5 years for Cassini. At Jupiter, we conducted a very successful scientific flyby and flight test and hit the window to target us for Pluto encounter this summer. Following the Jupiter flyby, we spent 8 years crossing 2.5 billion miles of space to the farthest shore that humankind has ever explored. Now, I have to say, it took 26 years to go from the first Mariner mission to Venus all the way to Neptune. And it was another 26 years before we flew this mission. In 1990, the U.S. Postal Service issued a set of stamps commemorating the first missions to every planet. And if I can have the next time step, the only one for Pluto they could come up with said not yet explored. We flew one of those stamps on New Horizons to Pluto, and 2 weeks ago today we canceled it. So we really did it. This was an amazing team of people, and if I can have the next view graph, let me show you the Pluto system. This is their first trip to a binary planet. Pluto on the left, its large moon Charon on the right for scale. The diameter of Charon is almost precisely the diameter of the state of Texas, by the way. Pluto's about the diameter of the United States, and you can see they're very different. Charon has no atmosphere. It has no substantial volatiles on its surface. It's much darker and less reflective. It is not colored. How these two came to be is a mystery to us. Why they should have traveled together for so many billions of years and yet been so different is unknown. And that is part of the power and the attraction of planetary science, because we are exploring the unknown. Next time step, please. Well, this is Charon up close, as seen by New Horizons. You can see it's a pretty battered world. It's covered in water ice. It's got a strange dark pole, you can see there, that we informally call Mordor. Large chasms. You got to engage the public. Large chasms, and these craters are going to tell us a lot about the population of the Kuiper Belt. Perhaps I can answer more questions about Charon later. Let me show you the star of the show. Next time step, please. This is Pluto in false color on the right and accurate color on the left. This is one amazing world, and we really don't understand how a world of this complexity can have come to be and still be active today 4 billion years after its formation. We have a lot of work to do to understand this. I can show you some close-ups from the encounter. That's the next time step. Here are just two of many close-ups to come. These are already on the ground. Both of those scenes are about 250 miles across. On the left is the discovery image that gave us evidence for nitrogen glaciers, perhaps liquids flowing under those glaciers on Pluto, 400 degrees below zero. Absolutely amazing. And on the right...
Dr. Stern, are these photos that no one has seen before? I understood you had a couple of these. Maybe those.
These all came down last week, and they
okay.
have been released before,
Okay.
sir. On the right is a mountain range, which we informally have named for Tenzing Norgay. We often call Pluto the Everest of planetary exploration, and we have named the two mountain ranges that we've discovered for Hillary and Norgay. These are about as tall as the Rockies. We are continually surprised by the data that's coming down. There is now evidence for an internal ocean in Pluto and perhaps another at Charon, evidence for global change, evidence for atmospheric hazes, and many other wonders. I have to say, with only 5% of the data on the ground, we all feel like we need to fasten our seatbelts for the remaining 95%. This is quite a ride scientifically. Now, if I can turn to the next view graph, I want to say that there was a tremendous public response to the flyby of Pluto. This is a scene from the Johns Hopkins Applied Physics Lab where thousands of people came out to celebrate that encounter. But next view graph, I think even more importantly, there's the cover of the New York Times, and below it, little postage stamp images. I'm told that almost 450 newspapers put New Horizons and the exploration of Pluto on the front page the day after the flyby, that there were over 12 billion web hits, and that I know that there were 5 television specials, 1-hour-long specials made about this mission. People love exploration. That's the takeaway that we get. They really love it when we go new places and make new discoveries and do bold things. And I think the viral response of the media and the public to New Horizons is a testament to that and what we can do in NASA in the future. Let me close with the next view graph. I was asked to say a word or two about a possible extended mission for New Horizons. The spacecraft is healthy and full of fuel and fully capable of flying a mission to explore further in the Kuiper Belt. We have 2 potential targets, and working with NASA, we expect to choose between them later this summer. The National Academy of Sciences highly recommended this portion of the mission after Pluto through the decadal survey process, and we're going to propose it for funding to NASA next year when NASA makes that call for proposals. I'll take my last chart, and I want to show you an image that's of special significance, not because of the scientific discovery of hazes in Pluto's atmosphere that this reveals. I'm sure many of you remember the iconic Apollo image of Earthrise over the moon, which was so iconic because it proved that the astronauts were there. It was a view that you could only get from being in orbit around the moon. Well, this image is taken from the far side of Pluto, looking back to this planet silhouetted by the sun. It is proof that we went there, that we are now on the far side of Pluto, and that our nation can do great things. Thank you.
Thank you, Dr. Stern. Just fascinating. Dr. Russell.
Thank you, Mr. Chairman, for providing me an opportunity to review Dawn's recent scientific discoveries, to explain their relevance, and to discuss future missions. I'd like to begin with a few words about Dawn itself. Dawn is the 9th mission in the NASA Discovery Program. These missions are principal investigator-led, they are relatively low cost, and are focused investigations selected by peer review from proposals submitted by planetary scientists. Could I have the first graphic, please? This shows the Dawn spacecraft, artist's conception, at launch from Earth in 2007. Dawn has achieved several important firsts in space exploration. It's the only spacecraft ever to orbit 2 extraterrestrial bodies beyond the Earth, and only to orbit an object in the main asteroid belt between Mars and Jupiter. Moreover, Dawn was the first scientific mission to use solar electric propulsion. Because electric propulsion thrusters accelerate the fuel over 10 times faster than chemical engines, smaller launch vehicles and smaller spacecraft can be used to do more exploration. This has enabled Dawn to visit the giant protoplanet Vesta, which was a fascinating world closely related to the terrestrial planets, and more than typical asteroids. It's more of a planet. And then to travel to Ceres to enter Ceres' gravitational field and to begin to map this dwarf planet. By using the new technology of ion propulsion, we've accomplished more than we would have been possible with conventional technology, and done so at 1/3 of the price. Could I have the next graphics, please? This shows how we map. We go into a high altitude circular orbit and then move in closer and closer, getting higher resolution. And on the right-hand side is a color picture made by stretching the color images that we got from the camera. We also, besides taking pictures, we measure in the visible and infrared spectra and look at gamma rays. We measure the gravitational field to get the mass distribution of the body, and also look at the elemental composition. In 2012, Dawn completed its measurements at Vesta, which was the 2nd largest body in the asteroid belt, and then we validated the model of the solar system evolution that had been developed from meteorite evidence by validating that the meteorite evidence had been correct. We learned much about Vesta, and we believe that Vesta was a precursor to the bodies that form the Earth, that the bodies that in the asteroid belt, many of them accumulated to form larger bodies. The Earth's core may have first been formed in smaller bits in the Vesta-like bodies. Next graphic, please. This brings us to Ceres. We have a color map of the surface. This is stretched, but it shows the diversity of processes that must have been going on within Ceres. And on the right, we have an elevation topography of a section of the surface, and it's much more muted than Vesta was, as if that we have a lot of erosion on the surface, much like Mars. Then we now are looking at Ceres from about 4,000 kilometers. We are now moving down to get higher resolution. Next graphic, please. This shows two of the more famous landmarks. The first on the left-hand side is the Okatar crater with bright spots. We believe these are salt left by evaporating water, as occurs in the Earth's deserts. This evaporation also makes a haze layer that we can occasionally see in the crater. We've got other features that look like pingos. On the right-hand side is this small mountain about 3 miles high. It's got some dirt on it, but it looks like it has ice coming down the sides. We were totally surprised by the Pluto observations that showed mountains on Pluto that were very much like this mountain that I show you here. We have 2 more orbital phases for Ceres. We'll go down to as low as 200 miles above the surface, get gravity field measurements and the elemental composition. And then we will park the spacecraft in a stable orbit to protect it from crashing into the surface. Ceres is an object with potential biological interest. It's got water and heat from the sun and the interior. The astrobiological community is very interested in Ceres. We've shown that Ceres is relatively easy to reach with a significant payload if you use ion propulsion. Ceres has a much lower gravitational field than Mars, and the thrust needed to land is much less, so landing is very feasible. Rover missions, landers such as the upcoming InSight mission to Mars are all possible and highly desirable. We believe that Dawn, with its small exploratory payload, has only scratched the surface, so to speak, of what could be done. I'd like to close with a brief but heartfelt thank you for you and your support of a strong space program. This support has brought a treasury of knowledge and a legacy for future generations. Thank you.
Thank you, Dr. Russell. Dr. Papalardo.
Chairman Smith, Ranking Member Edwards, and other members of the committee. I'm very happy to appear before you to discuss NASA's Europa project. I note that I do so as an employee of the Jet Propulsion Laboratory, which is a federally funded research and development center managed by the California Institute of Technology for NASA. Jupiter's moon Europa is one of the most likely places to find current life beyond our Earth. For over 15 years, NASA has studied a variety of mission concepts to explore Europa and determine if it could be habitable. My own fascination with ice-covered moons of the outer solar system blossomed in 1985 with a seminar course at Cornell University taught by Carl Sagan entitled Ices and Oceans in the Outer Solar System. Though I was just an undergraduate, Sagan allowed me to audit this graduate course. In some sparkling moments, Sagan was as brilliant a teacher as one could imagine and inspired what would become my career. I joined my first Europa mission science definition team back in 1998. Now working at NASA's Jet Propulsion Laboratory, I'm the project scientist for the burgeoning Europa mission, serving as the interface between the engineering team and the recently selected science team. In the late 1990s, NASA's Galileo mission to Jupiter produced strong evidence that Europa, which is about the size of Earth's moon, has a global ocean beneath its frozen crust. This ocean could contain more than twice as much water as Earth, with abundant salt water, a rocky seafloor, and chemical energy that could potentially be transported to the ocean by processes powered by tidal heating. Europa might have the ingredients necessary to support simple organisms. Europa's rich and diverse geology and its probable subsurface liquid water ocean are both believed consequences of the strong tides that heat the interior and flex the surface to its breaking point. Europa's chaotic terrains, which are regions of disrupted surface ice, display similarities to features in Antarctica, suggesting that they could be surface manifestations of shallow subsurface lakes. If that's true, these lakes are possible abodes for life at Europa. Europa's chaotic regions are commonly brownish-red in color with infrared signatures that are suggestive of salts, probably derived from the ocean below. NASA's Europa mission plan calls for a spacecraft to be launched to Jupiter in the 2020s, arriving at the distant planet after a journey of several years. The current plan envisions a spacecraft that would have an expected lifetime of more than 3 years and would orbit the giant planet about every 2 weeks, providing many opportunities for close flybys of Europa. During these flybys, the spacecraft would achieve near global coverage, image the moon's icy surface at high resolution, and investigate its composition and the structure of its ocean and icy shell. NASA announced the instruments for the Europa mission's scientific payload on May 26th. The payload of 9 selected science instruments includes cameras and spectrometers that will produce high-resolution images of Europa's surface and determine its detailed composition. An ice-penetrating radar can determine the thickness of the moon's icy shell and search for subsurface lakes, similar to those beneath Antarctica. The mission also will carry a magnetometer to measure the strength and direction of the moon's magnetic field, to allow scientists to probe the thickness and saltiness of its ocean. A thermal instrument will scour Europa's frozen surface in search of recent eruptions of water or warm ice, while additional instruments will sample tiny particles of water, dust, and plasma in the moon's extremely thin atmosphere. NASA's Hubble Space Telescope observed water vapor above the south polar region of Europa in 2012, providing tantalizing evidence of water plumes. If plumes are confirmed, and if they can be linked to the subsurface ocean, they'll allow us to interrogate the chemical makeup of Europa's potentially habitable subsurface environment while minimizing the need to drill into the ice. Just last month, NASA completed its first major review of the Europa flyby mission, which has now entered the development phase known as formulation. During the remainder of 2015 and through FY 2016, the project will work to develop science requirements, mission architecture, planetary protection requirements, risk identification and mitigation plans, cost and schedule estimates, as well as payload accommodation for the instruments for the mission to Europa. In short, NASA is formulating a project that could lead to fundamental discoveries about Europa. This will be both an ambitious and an exciting undertaking. Just as with that graduate Carl Sagan course I took at Cornell, this mission will be at the cutting edge of science and engineering and is sure to inspire the next generation. Thank you, and I look forward to any questions.
Thank you, Dr. Papalardo and Dr. Braun.
Mr. Chairman, Ranking Member Edwards, and members of the committee, thank you for the invitation to share my views of the exciting future of America's solar system exploration program here today. I'm the engineer at the table, and I must say it's an honor to be seated here with some of the world's planetary science luminaries. I've been a faculty member at the Georgia Institute of Technology since 2003, and judging by the passion and creativity of the students that I see every day on campus, I'm confident that the grandest era of space exploration lies ahead of us. I presently serve as Vice Chair of the National Research Council's Space Study Board and Chair of NASA's Standing Review Board for the 2020 Mars Project. However, I'm here today as an individual, and the views I express are mine alone. Planetary science is one of America's crown jewels. These endeavors have consistently reminded people worldwide that the United States was not just founded as a bold and curious nation, but continues to lead in discovering and exploring the richness of the worlds beyond our own for the betterment of all. Beginning more than 50 years ago with the Mariner 2 mission to Venus, the United States has consistently led the exploration of our solar system. Decade by decade, we have designed, built, and operated a balanced portfolio of missions targeting destinations across the solar system. Today, as we celebrate successes like New Horizons' visit to Pluto and Dawn's mission to Vesta and Ceres, another U.S. spacecraft is on its way to Jupiter, 2 U.S. rovers trundle across the Mars surface, and U.S. orbiters at Mars and Saturn are returning tantalizing insights. And yet, there are still so many questions to answer. We now know of a multitude of ocean worlds in our own cosmic backyard. This list obviously includes the Earth, but also Jupiter's moons, Europa, Ganymede, and Callisto, Saturn's moons, Enceladus and Titan, and Neptune's moon, Triton. Enceladus and Europa may be the 2 worlds in our solar system best suited to search for life as we know it, whereas Titan is likely the best place to search for life as we don't know it. Accessing the water within these ocean worlds should be one of our next great planetary science quests, one with ramifications for understanding the emergence of life on Earth and the potential for life elsewhere. That's why it's surprising today, even considering the work being done towards a mission to Europa, that there are no planned missions in NASA's planetary science portfolio to access the water in locales where we know it to exist. Because the transit times, distances, and radiation and surface environments of these ocean worlds differ so significantly from vistas we have previously been, new engineering capabilities and technologies must be developed, particularly if we want to land, rove, or dive within the ocean worlds. Fortunately, many of the needed technologies, including advanced power systems, radiation protection, sensing, landing, navigation, and communication technologies, were included in the 2015 House Appropriations Bill for NASA. Through these investments, the number and capability of missions to the outer planets is poised for growth. NASA has a successful track record in the development of game-changing technologies to enable planetary science. Were it not for the successful technology demonstration of solar electric propulsion by the Deep Space One mission in the late 1990s, Dawn would not likely have been selected as a discovery mission. This technology has since been commercialized to the benefit of the U.S. satellite industry. As a result of NASA's high-efficiency solar cell technology investments, the Juno mission is now en route to Jupiter. It's the first solar-powered spacecraft to travel beyond Mars, a region where nuclear power had previously been required. This technology is now making its way onto other science missions, including the Europa mission, and is affecting our solar power infrastructure here at the Earth. These examples demonstrate that development efforts external to flight programs can be effectively used to retire new technology, risk, and cost. In fact, removing technology development risk from its flight programs has been cited numerous times by the Government Accountability Office as a means to better manage NASA's spaceflight missions. Humanity should be proud. We've now completed a first investigation of each major celestial body in our own solar system. Now is the time to accelerate the pace and the scope of our nation's solar system exploration program. Let's sample the water of our solar system's ocean worlds. To do so, we must couple our scientific drive with investments in the critical space technologies required to accomplish these goals. Underscoring our country's scientific prowess, engineering creativity, and technological skill, this is a journey sure to inspire the world. Thank you again for the opportunity to be here today. I look forward to your questions.
Thank you, Dr. Braun. I'll recognize myself for questions, and Dr. Grunsfeld, let me address the first one to you. And that is, if Congress restored the proposed $70 million in cuts that the administration has recommended for planetary science, what could you use that money for, that $70 million?
One area that the Decadal Survey prioritizes, as do we pretty highly, is our Discovery and New Frontiers program. As you know, the Pluto New Horizons mission was the first in our New Frontiers program, and wildly successful, I would say, is an understatement. And we are just in the process now, hopefully in September, before the end of the fiscal year, selecting investigations for the next Discovery program. And so we would be able to keep those on track and increase the cadence with increased funding.
Thank you, Dr. Brunsfeld. Dr. Stern, let me offer you a slow pitch over home plate. And what do you think is the greatest discovery of the many discoveries made by New Horizons so far?
If you'll allow me, Mr. Chairman, I'd like to suggest that there are two very important discoveries. One is scientific, and that is the one that I alluded to, that it's very clear that we do not understand the interior workings of small planets. Previously, we'd found many active bodies, satellites, for example, of the giant planets that showed activity after these many billions of years. But we always had an out scientifically in that they derived their energy in large measure from tidal heating, which is specifically a result of being in orbit around a giant planet and in a giant planet satellite system. Pluto is completely isolated. It does not generate any tidal energy with its interactions with Charon because they have reached tidal spin equilibrium. And yet somehow this world is active after 4.5 billion years. And just like a small cup of coffee will cool off much more quickly than a big vat of coffee, small planets should cool off, and yet it has not. And this is a major challenge to the field of planetary science to understand how this can be, and it's a demonstration that only could be made by going to Pluto, which New Horizons has now done. I want to say the other big discovery, in my view, is a level of public interest in exploration, which went completely viral. Yeah. I think people really like frontiers, and the United States is in a great position to extend soft power projection through just this kind of space program.
Yeah, I agree with you. I love to see the media coverage, and it shows that people are fascinated by exploration. I liked your turn of phrase a while ago, the power and attraction of exploring the unknown, and I think that does appeal to people. Dr. Russell, NASA is tasked with the responsibility of cataloging our near-Earth objects with diameters greater than 140 meters. In what way does the DAWN mission help us understand both the risk and the possibilities of detecting those near-Earth objects?
Dawn is far out of the line of fire, so it does not really add very much to that particular objective. However, that there are a lot of things we are doing both by observations from the Earth and observations from space that will enable us to solve those particular problems. But Dawn is more in the area of what Dr. Stern just told us about, is trying to understand how those mid-sized bodies were formed and still are active today in the case of Ceres and a little bit in the case of Vesta too. So we're really looking at a spectrum of bodies in the solar system.
Okay, thank you, Dr. Russell. Let me address my last question both to Dr. Papalardo and Dr. Braun. And this question is asked not only on behalf of myself, but on behalf of my Texas colleague, John Culberson. I don't know of any member who has a greater interest in Europa than John does, as you probably know and probably have talked to him about it firsthand. But the planned mission to Europa is in part, I think, designed to try to detect any possible form of life. And Dr. Braun, you mentioned the need to explore our ocean worlds. I think Europa offers one of the best possibilities of doing that. Dr. Papalardo and Dr. Braun, how could that mission to Europa inform our understanding or enable us to perhaps ferret out any type of form of life there?
What we really are trying to get at Europa first is it a habitable environment? We think it is. We want to understand the potential ingredients for life. We want to confirm an ocean. We want to understand the chemistry and whether that is conducive to life. And we want to understand, is there an energy source for life in Europa's ocean? And by that, I don't just mean tidal energy, but is there the chemical imbalance that can allow for chemical reactions to power life? This mission wouldn't really go to search for life exactly, but to understand the habitability, kind of like the initial Mars rovers did. At
Right.
Mars.
And Dr. Braun?
Yeah, the Europa surface is planetary science Disneyland. And flying above it and studying it from above is like taking a 3-day drive across country from here to Disneyland and staying in the parking lot. Right? So I believe strongly, just like in our Mars exploration program, we've had orbiters and we've had landers. And the two together have what's advanced Mars science. So if we truly want to advance Europa science in the same way, it's going to take a combination of flyby/orbiter and landed assets.
Both. Okay.
Until we touch the surface, we won't know.
Okay. Thank you both for your responses. And the gentlewoman from Maryland, Ms. Edwards, is recognized for her questions.
Thank you very much, Mr. Chairman, and thank you to the witnesses. I have to tell you, I feel like highly undereducated here today. And I hope that the young people who are watching and listening and those who are here understand that today we have some of the most amazing planetary science minds available in the world, and it's just a delight to be able to have you here with us today. I've been very curious in looking at the life cycle of projects and missions, because I think here in the Congress sometimes we deal with things that are very, very short term, and we're thinking about, the next appropriations cycle, a year or 2 years. And it occurs to me as you're talking about each one of these missions that, in fact, going back to the recommendations that come out of the decadal survey and the work that actually precedes that, so that something actually makes it on a list to the time that we do all of the work that it takes from a scientific perspective, from an engineering perspective, to get a mission underway, and then to look at the results and figure out what's next. It's a really long life cycle, and I appreciate your sharing with us today, because I think sometimes we don't understand that it's a long life cycle, and we have no idea sometimes at the end or the near end what we may have been able to discover or predict at the beginning. And from a funding standpoint, and we've all talked about this, I think the chairman has mentioned it as well, it becomes hard to project what it is that we believe we're going to get for the dollar that we spend. And so I would like each of you, if you could, just take an opportunity, beginning with Dr. Grunsfeld, to talk to us about that life cycle and about the recommendations that come out of the decadal survey and how that's used and how we use the work of the academies to inform what we're doing, even if we can't see it for 25, 30, 50 years in the running.
Well, thank you very much. Certainly we rely very heavily at NASA in science on the community consensus that's built in the process of developing the decadal surveys. And in the last couple of planetary science decadal surveys, we got really excellent advice. The Pluto mission was highly ranked, and we've now achieved that, and it's continuing on into the Kuiper Belt to make new discoveries. In more recent years, a Mars sample acquisition mission was the highest rated objective, and of course we started that. That's the Mars 2020 mission. And the second highest priority in the flagship class missions was a Europa mission to go and study Europa, and we've now started that. And then cadence and discovery and new frontiers, which we've talked about, and research and analysis. And so we're doing our best to try and select this year discovery missions to go on for the next phase. It'll be a two-part competition. So we do rely on that, and I think the report card is we've been doing a pretty good job, and the science has been really spectacular.
Thanks. So, Dr. Stern, maybe you could tell us, I understand that in the early 2000s, NASA actually canceled a previous mission concept in exploring Pluto because of anticipated cost, and a New Horizons mission that actually almost never came to be. Can you tell us what turned that around? What are the lessons that we learned, and what are your reflections had we not been able to go forward from that point?
Well, thank you very much for that question. It is true. There were a series of Pluto missions that were studied but never started, in large measure because those missions got a little bit out of control on cost, and the agency had to make fundamental decisions about executing the remainder of the program. When the last of those was canceled in 2000, there was a tremendous public outcry. The Planetary Society, individuals in the public, big letter writing campaign, and a very strong response from the advisory committees to the Science Mission Directorate and its predecessor, the Office of Space Science, which convinced the agency to instead compete the mission. And it was a result of that competition that New Horizons came to be. We proposed that as a team between the Southwest Research Institute and the Applied Physics Lab of Johns Hopkins University. However, the funding that enabled the build and flight of New Horizons only came as a result of a recommendation from the decadal survey that this should be #1 on the runway for medium priority missions, the so-called New Frontiers missions that Dr. Grunsfeld referred to. So in my view, the decadal survey process is very important, but it's also very impressive how well it works within the political and policy sphere as well. Because when that mission was recommended as a top priority, it did unlock the funding that made this possible. And as you can tell, both from the standpoint of public interest as well as the general good feeling in the public about our being able to accomplish important things in our time, as well as the science that's coming out of New Horizons, none of those three things would have been possible had it not been for that decadal survey and the competitive process that we were able to win as a result.
Thank you very much. Thank you, Mr. Chairman.
Thank you, Ms. Edwards. The gentleman from Oklahoma, Mr. Lucas, is recognized.
Thank you, Mr. Chairman. Dr. Stern, I represent the northwest half of Oklahoma. And while we live on a very watery planet, water is always an issue of great importance in my neck of the world. Discuss for me a moment this appearance. It appears that we have a mountain of ice water perhaps on Pluto. I mean, from my perspective, from the perspective of my constituents, with a long enough timeline, anything's possible if you have water. Talk for a moment about the significance of this find.
Sure, happy to. Well, let me start by saying, prior to the arrival of New Horizons, the best imagery that we were able to obtain was using the Hubble Space Telescope, and thank you, Dr. Grunsfeld, for making that possible. Those images had a resolution of several hundred miles per pixel. We're now in the ballpark of several hundred meters, and New Horizons has data on board that are still substantially better. The very first medium resolution images that we returned just days after the flyby revealed steep topography on the surface of Pluto, those mountains. Now, the primary chemical constituent on the surface of Pluto is molecular nitrogen, condensed, the same stuff that we're breathing right now. That's a very soft material, and it can't support strong topography. The inference of the steep topography is there must be a much stronger material that can support mountain building and construction. And water ice is really the only plausible candidate for that in the Pluto system. We've known for a long time that probably a third of Pluto's entire mass is water ice. But this has taught us is that ice is very close to the surface, and that the nitrogen and the other things that we've observed spectroscopically are just a frosting, a veneer, if you will, on the top, and the water lies right below.
That said, you mentioned to the continuing mission of New Horizons, based on the fuel system in it, how long will the vehicle be viable as it continues? How many years would you guess the viability of New Horizons to be?
Well, New Horizons is very healthy. We have a spacecraft that features completely redundant avionics, propulsion system, and other features, so that it's very reliable, and we're not using any of the backup systems. Our primary limitation on New Horizons is a result of the radioactive decay of plutonium that powers the spacecraft from an electrical standpoint. Currently, that device is generating about 200 watts of power, and it's decaying at the rate of about 3.5 watts per year, which is exactly as predicted. New Horizons can operate from that device for about 20, possibly a little longer, years into the mid or late 2030s. Our extended mission, by contrast, would involve a flyby of a Kuiper Belt building block of planets like Pluto in 2019, so well within our capability.
One last question, I direct it to the whole panel. We talk about the great success of putting landers on the various planets and the potential to address the potential oceans that might be under Europa and other planets. discuss for a moment the protocols that we use so that we don't seed planets as we go along, so to speak, so that we don't take things with us when we get there.
So we have, I don't want to speak too much requirements, but we have actually a planetary protection program and documents and a planetary protection officer that review the missions. And it's particularly important for missions like Europa, for our Mars landers. We're having a discussion now about the cleanliness of Mars. Curiosity's wheels, so that we might go to some place that potentially has signs of liquid water. And so we analyze that in great detail. We clean the spacecraft, and we try and do our best not to send Earth life to places that it might be able to take hold. It's a big deal for us.
And in the water world, even a greater issue, correct, Doctor?
Yes, so for Europa, the plan is to bake the spacecraft, to heat the spacecraft and its components to a temperature that would kill off any microorganisms that might be on board, and the same for the instruments, and that, of course, has to be done in a way that is safe for the instruments, that it doesn't damage them, and then we protect the spacecraft and keep it clean before launch.
Thank you very much, gentlemen. Yield back my time. Mr. Chairman.
Thank you, Mr. Lucas. The gentleman from Colorado is recognized for his question.
Thanks, Mr. Chair. And gentlemen, when we applauded the New Horizons flyby of Pluto, the applause really goes to all of you. I mean, I know personally I'm just very proud of what NASA's been doing and about the exploration of our solar system and hopefully someday our universe. And the comments that all of you have made about us being explorers in our hearts. It's part of our DNA as Americans, I think as humans. And just thank you for being at the forefront of all of this. I'm basically speechless in terms of asking you the right questions. I'm very happy that a couple of you have solid connections to Colorado and to the University of Colorado. That's one of my favorite things. I guess the question I'd like to ask is, as we do these things, do you have students? Do you have people following in your footsteps? Because this seems to be moving at greater and greater speeds as we're going farther and farther with our exploration, or more focused with our exploration. So Dr. Pappalardo, Dr. Braun, why don't I start with you guys, and then I'm going to work to the other end.
Sure, absolutely. I have a laboratory of several interns, summer interns right now back at the Jet Propulsion Laboratory, who is hopefully watching this on the web, and who are extremely excited about Europa. There are some folks who have come here today from the Air and Space Museum who are interns, who are very excited about it. The students who are in elementary school today will be in graduate school at the time that this mission is probably arriving at Europa. And those are the folks that this mission is really for. Those are the folks we want to inspire and get involved as the next generation of explorers.
Thank you. Dr. Braun?
Yeah, if I could add to that, as a faculty member in the College of Engineering at Georgia Tech, I can tell you with certainty that these kinds of missions, whether they're at Mars, whether Europa or Pluto, they're a natural draw to more and more students in engineering and in science. They inspire young people into educational paths and
They even
careers.
inspire lawyers like myself.
Well, so we can get one or two of those as well, but we want more and more engineers and scientists.
Okay.
If that's okay. But there's no doubt that at Georgia Tech and at universities around the nation, that young people are watching, and that young people are inspired into our space program because of these types of feats, and that they lead, frankly, to economic, national security, and a large range of societal benefits as well.
Thank you. Thank you. Dr. Stern, it's good to see you. I don't even know where to start on the Pluto mission, other than that mission started when I started running for office 9 years ago. In the process, let's talk about the engineering, and Dr. Braun, you're welcome to chime in here, but the engineering is a marvel for me. The fact that basically the math, the science, the engineering all came together for you to hit a spot out there that's like a millimeter across, and me being able to hit it on that wall. I mean, can you talk about that a little bit, those parts of the mission?
Well, thank you very much, Congressman Perlmutter. The New Horizons mission is a technological marvel in miniaturization in terms of the accuracy of the flight path that we had to hit. We had to fly through a 60 by 90 kilometer window after a 3 billion mile journey. That's about equivalent to throwing a ball from Los Angeles to New York and landing in
the strike zone.
A can of beans.
Oh.
And we were a little bit early arriving. After 9.5 years, we arrived 91 seconds early, which is equivalent to L.A. to New York on a commercial airliner, 4 milliseconds off schedule. It's an amazing testament to the technology that's been developed in terms of ground-based tracking as well as the spacecraft technology that we can do these things and that we can miniaturize the instrumentation to this level and that the spacecraft can fly autonomously using hibernation techniques as if it has an onboard intelligent pilot. All of those things and more are amazing aspects of the technology we developed. But most impressive to me is the fact that New Horizons was developed and flown in its entirety, soup to nuts, for 1/5 of the cost of the Voyager program on an inflation-adjusted basis. So we have really learned to do these things in NASA that are not only technologically impressive, but get a lot more bang per buck than at the outset of the space program.
And my time has expired. I'll yield back, but Dr. Russell, Dr. Grunsfeld, thank you too. I'll get you next time. Thanks.
Thank you, Mr. Perlmutter. The gentleman from Oklahoma, Mr. Bridenstine, is recognized for his questions.
Thank you, Mr. Chairman. What an exciting testimony from all of you. I'm thrilled about it as a member of this committee. I wanted to ask Dr. Grunsfeld, I read in Space News recently about this cryogenic compressor assembly for the James Webb Space Telescope. And it's been delayed, and of course the costs have gone from $22 million to $150 million. I was wondering, can you shed light on how that happened and ultimately what the impact that will be for the James Webb Space Telescope?
Sure, I'd be happy to. First of all, I'd like to report that the cryocooler assembly has been delivered on dock to JPL. I think that was 2 days ago. I was just trying to remember. It might have been 3 days ago. And so it's complete. It's been delivered from Northrop Grumman to JPL. JPL will do the acceptance testing, and then it will be delivered to the Goddard Space Flight Center and integrated in with the rest of the assembly. First of all, the James Webb Space Telescope we talked about technological tour de force. The number of inventions that had to occur to be able to build the telescope, and now they're all complete, was really phenomenal. This is a telescope that will go 1 million miles from Earth and will achieve a temperature, the actual optics and the instruments, that's roughly the temperature of Pluto. And it needs to do that to be able to see these very dim objects at the edge of our universe and to study exoplanets. One part of that was this very innovative cryocooler. The team that proposed it built an engineering unit which was bolted together and showed that they could make a cryocooler to get these cold temperatures. What they failed to do was to demonstrate they knew how to manufacture one for flight. So it was bolted together instead of welded. Some of the materials were different. And in the process of figuring out over the better part of a decade how to actually manufacture it for the flight unit, they encountered a lot more difficulties. Thank you very much to Congress for funding us appropriately to be able to afford the spending on that cryocooler in our reserves, in our unfunded part of the budget, so that we could accommodate this problem. Other problems, other assemblies went smoothly, and so we applied our reserves on this, and it's since been delivered. So we're past that.
And
it really
I wanted
was the difficulty of manufacturing.
To ask on that point that you made regarding funding, it looks like funding for next year for the James Webb Space Telescope is being cut per the President's budget request by $25 million. Is that, and of course the money is going other places. Is that a problem for this issue? Are we gonna have more issues like this where we have unexpected costs that creep up? I just don't want to put the James Webb Space Telescope at risk.
Yeah, me neither. It's a very high priority for us. It's going to make amazing discoveries. One of the things that the James Webb Space Telescope will be able to do is follow up on the Pluto New Horizons observations as it goes sailing off into the Kuiper Belt. The President's proposed budget is exactly what the project asked for. So that's just the normal change in budget as they retire some of the development activities and go into integration and test. So we actually asked for exactly what we need, and we got that as a request.
Okay. Well, that was my major question. Thank you for answering, and thanks, Chairman.
Okay, thank you, Mr. Bridenstine. The gentleman from Texas, Mr. Babin, is recognized.
Yes, sir. Thank you, Mr. Chairman. What a fascinating, probably the most fascinating committee meeting that I've been to in my congressional career so far. And Dr. Grunsfeld, let me just say congratulations to all of you for playing a part in this huge endeavor that we've just seen a successful into. Actually, kind of a beginning to. But Dr. Grunsfeld, the Johnson Space Center, which I represent in Houston, is home to the Astromaterials Acquisition and Curation Office. This office is responsible for the curation of extraterrestrial samples from NASA's past and future sample return missions. Their mission includes the documentation, preservation, preparation, and distribution of samples from the moon, asteroids, comets, the solar wind, and the planet Mars. Would you please explain how this facility will contribute to future planetary science missions going forward, and how this unique and important capability will be maintained?
This Astro Materials facility at the Johnson Space Center really is a national treasure. As you said, this is where our moon samples are kept, mini meteorite samples, samples from comets will be stored there. Our OSIRIS-REx mission is going to perhaps return as much as 1.2 kilograms of samples. We're partnering with the Japanese on their sample return mission, and we'll have exchanges of materials. This is, really our treasure trove of, deep space samples. And our Mars 2020 rover, which will be collecting samples, eventually we hope to get those back to Earth, and that'll be the center of activity. And so it really is a science warehouse, if you will, as much as the data that comes back from Pluto New Horizons will be stored on servers. This is our central warehouse for that.
Right. Okay, thank you very much. I also have one more question for you, if you don't mind. NASA's Space Launch System, or the SLS, will be the most powerful rocket in the world and will carry humans on exploration missions beyond Earth's orbit. Given its tremendous lift capability, what advantages would SLS provide for planetary science, and what types of missions might be enabled by SLS? Although today I've heard that we don't need these huge machines as much as we have in the past with some of the lightening up of a lot of these instrumentation. But what is your thoughts on the SLS and what the capabilities of the future would be?
My view is that the Space Launch System will be transformative for science. And let me say that Pluto New Horizons, even though it was light-weighted as much as the team could do, still required the largest Atlas rocket that could be built. And to be able to get that speed to zip out to Pluto. The mission to Europa, we're currently designing the spacecraft to fit on any of a variety of launch vehicles, but we're including the Space Launch System in that trade space because the trip to Jupiter to get to Europa is a very long trip. On the biggest Atlas rocket, it would take just shy of 8 years to get to Europa, and zipping around the inner solar system, getting slingshot out. On the Space Launch System, it would be under 3 years. And this is one of those rare cases where time really is money, because in that extra cruise time, we have to maintain an engineering team and a science team and a spacecraft while it's in cruise, even if we hibernate it. And that's something that, also delays the science. A large launch vehicle like the SLS with a large fairing, the container that the spacecraft goes in, can also be enabling for things like deep space astronomy, launching a larger telescope, perhaps even launching telescope parts that astronauts could assemble to build a telescope that could search for atmospheres around nearby worlds.
And if I might, I don't want my earlier remarks to be misconstrued. I really appreciated your question, but let me say that for a mission like New Horizons, which is a simple flyby and first reconnaissance, that miniaturization really helps us. But for the next steps up, when you want to do orbiters and landers and sample return, like the ambitious missions that have been spoken about, you need to carry a lot of fuel. And there's no way to lighten the fuel. You need it so you can come to a stop on that planetary surface or in orbit. And SLS is going to really help us enable those kinds of deep space missions, including, I hope, one day a return to the Pluto system in the Kuiper Belt.
Thank you, Dr. Stern. I appreciate you making an addition to that. Appreciate all the witnesses. Very fascinating. Thank you so much.
Thank you, Mr. Badman. The gentleman from Ohio, Mr. Johnson, is recognized for his question.
Thank you, Mr. Chairman. Dr. Grunsfeld, I represent the 6th District of Ohio, and although NASA Glenn is not in my district, being the only member from Ohio on the Science, Space, and Technology Committee, I'm very interested in what's going on at NASA Glenn, and I know they've been involved in the past in the Advanced Stirling Radioisotope Generator program. There's concern in the science community about the inventory of plutonium-238, as you know, the fuel which powers long-distance robotic spacecraft. Last year, NASA canceled its program to design the Advanced Stirling Radioisotope Generator that would use far less plutonium-238 per mission. So in place of this program, what is NASA doing to develop the next generation of nuclear power sources for exploring the outer planets?
Thank you. First of all, what we canceled last year was the flight portion of the Advanced Stirling Radioisotope Generator, so a flight model to use on a mission. We've kept the technology funding so that they can continue to advance and do life testing on the technology. What we determined is that the cost was growing for the flight unit very rapidly, and it wasn't clear that it would converge, but we want to keep that technology going, so we're continuing to fund that. At the same time, we're working with the Department of Energy very closely on production of new plutonium-238. We have an existing stockpile, and the new plutonium will be mixed with the old plutonium to create fuel for future missions that could include Discovery, New Frontiers. We have enough fuel currently on hand for our Mars 2020 mission. We've made the decision, partly based on the great success of the Juno mission so far, to go with solar. It's actually a better match for the Europa mission, but we certainly are going to increase the production and maintain our capability for building our multi-mission radioisotope thermal generators. We're also investing in technology that will allow the current fuel to be more efficient, new thermocouples to up the efficiency. And all of that work, all of what I described, is being done at the Glenn Research Center.
Okay. Now, staying on the budget theme for a minute, how does the FY16 funding for NASA's Planetary Science Division impact? You mentioned the New Frontier program. How does it impact the scheduling of the next New Frontiers competition?
The next New Frontiers competition, we're hoping, actually Jim Green is here, we're hoping to put out a solicitation in roughly the next year. The funding level in the FY16 request doesn't allow us to be particularly aggressive, and so that's something that would then be launching sometime early in the next decade.
Okay, all right. And for any of the rest of you gentlemen, how have budget cuts to NASA's Planetary Science Division impacted the scientific community, particularly the next generation of planetary scientists? Anyone have a concern?
Why don't I say a word just for my colleagues who rely on the research and analysis program. There are a lot of young scientists who question whether they can stay in the field because of the kinds of cuts that have happened in planetary science. And then when we don't see new missions coming along, and finally Europa is coming along, we don't see the kinds of research programs that go along with those missions. So something like the Europa mission brings along with it a large cadre of science and some funding to do science and promote research in that area. But yeah, I just want to raise a flag regarding that research and analysis program, because there are a lot of excellent young scientists who feel like, well, maybe they should just leave this field.
Okay. Dr. Grunsfeld, back to you. NASA backed out of the ExoMars mission, leaving Russia to partner with Europe. NASA's InSight mission, as we know, is an American spacecraft, but it carries mostly European instruments. How is NASA's Planetary Science Division strategically approaching international cooperation on future missions?
I think, the first thing is that when we changed our participation in ExoMars 2016, the trace gas orbiter, and ExoMars 2018, their lander, we at the time were providing a launch vehicle, some instruments, and a landing system. In the tight budgets, it was decided that providing those capabilities really wasn't advantageous to the United States. However, we're still deeply involved in both missions. We're providing a lot of support. We're providing instruments, some technical capability for the Trace Gas Orbiter, and we're actually providing from the Goddard Space Flight Center the Mars Organic Molecular Analyzer, which is the front end for the highlight instrument on the lander. And so we have U.S. scientists deeply involved in the ExoMars, both 16 and 18 opportunities. And we're thrilled that the Russians have come on board, that it's now a stronger partnership. About 90% of all of our planetary science missions have significant international partnerships. And a good example is the Cassini spacecraft, which not only has scientists participating in multiple instruments, but they provided a whole probe, the Huygens probe, which descended into Titan's atmosphere. Okay. The Mars 2020 mission, again, a lot of international partnership.
I'd like to go deeper, but my time has over-expired, and Mr. Chairman, I thank you for the indulgence. I'll yield back.
Thank you, Mr. Johnson. The gentleman from New York, Mr. Tonko, is recognized.
Thank you, Mr. Chair, and thank you to a very distinguished and impressive panel of witnesses. And thank you for reminding me and hopefully all of us of where vision, leadership, and tenacity can truly take us. 46 years ago, the world watched as Neil Armstrong and Edwin Buzz Aldrin and Michael Collins' journey to the moon captured humanity's imagination and inspired a generation to reconsider the possibilities of space exploration. In those years leading up to the moon landing, I watched with great interest as a high schooler the race between the U.S. and the Soviet Union for space flight supremacy. Hearing and learning about the work you do, the matters you study, and certainly all of us were captured by this and are in awe of what we will explore and learn in the coming years. Back with the space race of the 60s, we had a young president who challenged the nation to land on the moon, and we had a passionate resolve to use science and engineering to beat our rivals. And it's been years of investing and innovating that enabled America to be a leader in this endeavor, to be the first to land on the moon and to continue with space explorations. One of my biggest concerns is that as a nation, we may be losing sight of what we can achieve in terms of space exploration, and that in turn we may be missing opportunities to inspire the next generation of scientists and engineers. We must retain the will to explore as well as the human infrastructure needed to make the proposed missions a reality. So for any of you, I would ask, do you believe that the public is aware of the many missions and discoveries that we're making as a nation? And I would reference this basic New Horizons Pluto mission. Is there that growing interest that we saw in the 60s, in your opinion?
Well, if I may answer that on behalf of my experience with New Horizons in recent weeks, I've seen a tremendous outpouring from the public, both in talks that I've given, like at the Intrepid Museum in New York this past weekend, as well as through email and social media. I've seen an enormous number of young people saying, I've never seen anything like this. We can do great things in our time. It makes me feel good about our generation, that we live in a time like this. And I've seen people actually tell me that they were moved to tears about the New Horizons flyby. I think we can inspire. And the program that's coming in the future, I think, can equally inspire.
Thank you. And anyone else that wants to offer anything
I would
there?
just say that when we landed the Curiosity mission on Mars almost 3 years ago, we had amazing response from the public. There were crowds in Times Square watching on the large screens. This is for an event as just a mission landing on Mars, not even the great science that came out afterwards. Because of the power of social networking, we have the ability now to measure the response for events like Pluto New Horizons, like the Mars Curiosity landing, even just announcements from NASA of discoveries of a cousin system to our own solar system, a sun like our sun and a planet somewhat like our Earth. And we find, that ridiculously large numbers of people are following this, and worldwide billions and billions of impressions. The circulation times the number of stories that far exceeds the number of smart devices and computers and phones and things. It's really quite remarkable. And what I think is most encouraging is that when we have an event like the flyby, that's excitement, that's exploration, that's the human endeavor, and we get this great following. What I find most encouraging is that once the science starts coming out, the following is still there. The inspiration is working.
Well, many are concerned about our underproducing the engineers we need for society here in the U.S. A commitment for this to continue and to grow in the exploration area smacks of research investment and human infrastructure development. What would you advise this committee, this panel, to do in regard to research investment and growing the scientists and engineers that we obviously will require?
Well, I'm very appreciative of the efforts of this committee and of the Congress in supporting our basic research activities. This is fundamental research, exploring the limits of human knowledge. But these are very hard things to do. Pluto New Horizons as a mission was a very hard mission to implement. When we try and do these very hard things, that's when we push engineers, push scientists to expand their own frontiers, which advances our nation technologically, industrially. This is one of the reasons why we do this and why it makes our nation so strong. A byproduct is it does inspire the nation and the world, which is also something we want to do.
Thank you. I believe I've exhausted my time, so I yield back, Mr. Chair.
Thank you, Mr. Tonko. The gentleman from Louisiana, Mr. Abraham, is recognized.
Thank you, Mr. Chairman, and certainly thank you, gentlemen, for being here. I'm privileged to be among rocket scientists. I guess the question to you, Dr. Grunsfeld, is first. NASA has a planetary science division, and certainly this research and these flybys and all this wonderful discovery that the panel has brought to light today ignites excitement and it stimulates young people. What programs does NASA have from the K-12 level, not only for the educators but for the students themselves, to continue that excitement and to get those engineers and scientists that you guys need?
Well, I think any of us would be very hard-pressed to go into a K-12 classroom and not see evidence that NASA's education programs, and specifically the education programs that we support in the Science Mission Directorate, that we don't reach from the scientist to teachers, master teachers, pre-service, in-service teachers, to the students in the classroom. We do this through both formal programs and informal programs. And so this is part of the DNA, if you will, of scientists that are funded by NASA programs. 20 years ago or so, NASA sort of had to twist scientists' arms to get involved in education. Now I find that young postdocs, graduate students, young professors, not only do they really want to involve themselves in the broader education effort, they want to do more than we can possibly fund, and they do. And it really is this broader public engagement that our scientists are doing that's part of the strength of the current science program at NASA. I don't know, Alan?
Well, I'll add, First of all, I'd like to echo everything that Dr. Grunsfeld said, but there are other aspects to this as well, and I'll just highlight two. One are the role models that we can provide from the science teams. When you have a viral event like New Horizons, our science team contains scientists, as young as in their mid-20s, brilliant scientists out of institutions like Stanford and MIT and other institutions that can go out into those classrooms and really connect. Those are role models. And then secondly, on New Horizons, we pioneered something very interesting. We are actually the first planetary mission to carry a student-built experiment, to give the students in that instance an opportunity not just to learn about how planetary missions are done and how the science is done, but to actually have a hands-on experience and ownership to fly something, in this case, across the entirety of our solar system and to make a little history.
Okay. All right, thank you. Just a quick question, and anybody can answer this. Going back to a previous question about international cooperation, what countries out there, besides, of course, the United States, are stepping up to the plate that will become leaders in exploration that you guys see coming down the pike?
I think in part because of the very strong cooperation that many countries have had with the United States, other countries, agencies of countries have been able to put together programs that are very strong, and in particular the European Space Agency, as evidenced by the recent Rosetta mission and the Philae lander on a comet. Incredibly exciting, daring, and successful. So there's no question that other countries aspire to have the kind of capabilities. I think one of the really important things is they aspire to do that, but they also look to partner with us. And I think as long as they continue to do that, we're in pretty good shape.
Okay. Anybody else? No? Okay. Dr. Grunsfeld, when does NASA anticipate requesting funding for another flagship mission? When do you guys see coming to the table again?
Well, certainly we've requested funding for the Europa mission, for the Mars 2020 mission. I think it's going to be the next decadal survey that cues up the priority for what we do after that. In the meantime, and it's already in our budget, we have some very exciting ideas for Discovery class missions that are in the queue, and we have certainly many ideas for New Frontiers missions. But I think with the Mars 2020 lander and the Europa mission, our ticket is pretty full right now, and it's pretty exciting.
Okay. Thank you, Mr. Chairman. I'll yield back.
Thank you, Mr. Abraham. It occurs to me I should have done it earlier, but I want to recognize a colleague of ours who has joined us, John Culberson of Texas, member of the Appropriations Committee. And as I mentioned a while ago, when I asked a question on his behalf about Europa, I don't know of anyone in Congress who has a greater interest in that moon than Representative Culberson. So, John, appreciate your being here today. This is indicative of his long-standing interest in space in general and Europa in particular. So, thank you for being here. The gentlewoman from Oregon, Ms. Bonamici, is recognized.
Thank you very much, Mr. Chairman, and thank you to the witnesses for being here. Good to see you, Dr. Grunsfeld. I apologize for not being here to listen to your testimony. I was in another hearing, but I did review it before the hearing today. And I understand somebody already asked the question. I was in the Education Committee, and I understand that somebody already asked a question about STEM education and workforce. So I'm going to ask you, we were all fascinated by the recent photos of Pluto beamed back by the New Horizons mission. It seems like we're making some incredible discoveries about distant bodies in our solar system at a regular pace, and that's really exciting for our country and our world. And although we continue to study our home planet to better understand and predict its changes, we've also learned that in some cases it's important to study Earth from a distance in order to understand its processes and mysteries. So how does what we're learning in the outer region of the solar system help us inform our understanding of Earth? Dr. Grunsfeld, would you please start?
Well, certainly. For all of our missions, we're observing our solar system in a snapshot of time. And, obviously we live on the Earth. We can go outside when we're not in rooms with all the shades closed. We can observe the Earth. And we can try and understand the geology of the Earth in great detail over past times. We can look at tree rings. We can look at glaciers. We can really try and put the picture together. But studying how other planets evolve, and we've usually have used Venus and Mars as sort of bounding cases of the direction Earth could have gone to try and understand the climates of other planets, the geology of other planets. And on Earth, there's really a unique thing, which is as soon as life emerged on Earth, it started changing the geology, the atmosphere, just microbial life had a really remarkable effect on the evolution of Earth. And so looking at planets like Venus and Mars, we don't know if there was ever life on Mars or if there is today. That's what we're trying to find out. It gives us a lot of information. There's also the question of fundamental questions. Where did we come from? How did the Earth get to be the way it is? And even studying planets like Mercury have helped us understand about the delivery of volatiles and organics. That's why, it's really exciting, and I'd like to pass on, if you don't mind, to Alan Stern to talk about Pluto, because, we sort of imagined that Pluto would be a frozen, somewhat dead planet, and we've discovered that it still has geologic processes and is, in some sense, as a planet, talking to the planetary scientists, is still alive and will tell us something, hopefully, about how the solar system was assembled.
Dr. Stern?
Well, thank you very much. And I have to say, when the National Academy's decadal survey process recommended Pluto New Horizons to the top of the queue, they pointed out two very important scientific problems that the exploration of Pluto could shed light on regarding our own Earth. And let me outline those for you. One is that the Pluto system as a binary planet is believed to have been formed through the same giant impact mechanism that the Earth-Moon system was formed. In fact, Pluto is the only place that we sent a spacecraft to, and the only place we know of that we can reach with a spacecraft that can shed light as a second example of a satellite formation system like shaped the Earth-Moon system. Very, very important. And if you have a chance to review the testimony that I made, I showed off the binary and what it can teach us about that just a little bit. Secondly, interestingly enough, Pluto's rapidly losing its atmosphere compared to most planets for a combination of reasons, one of which is that the upper atmosphere is pretty warm, and that speeds the escape. It turns out the escape process, which has a fancy name called hydrodynamic escape, that Pluto is suffering from in losing that atmosphere, is precisely the mechanism that took place early in the history of the Earth, when the Earth's atmosphere was made of hydrogen and helium, which are poisonous, and which led to the development of the current day atmosphere in part. This is not a mechanism that one can study anywhere else in the solar system on a planetary scale except at Pluto. So it's a window back in time into the early evolution of the Earth's atmosphere. And who would have thought that we had to go 3 billion miles to study fundamental aspects of the physics that have shaped our own planet, and yet we did.
That's great. I'm going to try to sneak in another question real quickly. Dr. Russell, now that Dawn has successfully proven the use of an ion propulsion engine for its planetary mission, what other potential science investigations could be enabled with this technology?
Well, the advantage of ion propulsion is that although it works slowly, it can accomplish the transport of large amounts of mass. So if you were taking some fairly large mission to Mars, for example, then it would be a very efficient way of transporting that material. But just going back to the asteroid belt, there are a lot of other asteroids there, and NASA's Discovery proposal queue is just full of asteroid missions, and many of them are employing or proposing to employ electric propulsion.
Thank you very much. I see my time has expired. I yield back. Thank you, Mr. Chairman.
Thank you, Ms. Bonamici. The gentleman from Alabama, Mr. Palmer, is recognized.
Thank you, Mr. Chairman. And this is for each member of the panel. Where do you need funding? And you don't have all day.
Yep. Well,
yeah, where do you need help?
Yep. Of course, the administration has made its request, and it funds all of the things that we've outlined in the congressional justification to fund. The place that we're still lacking is in the cadence of these new frontiers and discovery programs. And of course, as you heard, research and analysis funding is always appreciated by the community.
I'm here representing myself, and I wanted to bring up exactly the 2 points that Dr. Grunsfeld just did, that Dr. Papalardo did earlier. The research and analysis programs are crucial to understanding the data that comes back, because the ones and zeros themselves have no meaning. It's only with the application of bright scientists working on those data that we can actually turn those ones and zeros into discoveries. And then secondly, the cadence of Discovery and New Frontiers missions could be increased with the application of more funding, and very much to the benefit not just of the research enterprise, but I believe to the benefit of the United States and its standing in the world.
And I would just like to second what Alan just said. It's exactly right.
And I'll comment that the pace of Europa exploration depends on the pace of the funding. When we launch depends on the funding profile. And we can walk or we can crawl to get there.
Yeah, so I'll address that question as well, but maybe with a slightly different angle. All of the missions that we're talking about here today and all of the missions that we would like to do in the future hinge on technology readiness. And today there is a very effective partnership that has emerged between the Science Mission Directorate at NASA and the Space Technology Mission Directorate at NASA in creating the technologies needed for our future missions. So one of the things that I think is imperative for Congress to recognize and to recall is that without the investments in technology to enable our future missions, those future missions won't happen. And I can give you a list of 4 or 5 technology areas, some of which are actually included in the House Appropriations Bill.
As exciting as these missions are, and they're tremendously exciting, I'm from Alabama. As the chairman mentioned, we have this Marshall Space Flight Center. There's a lot of research going on in Huntsville and in Birmingham. As exciting as this is, though, I think one of the things that needs to be emphasized is the commercial and private sector benefit of what's being done through the space program. I mean, we've had tremendous advances in the quality of life because of these programs. How do you see these missions impacting that? Are there new technologies that you think will emerge out of this that are going to impact, that can be applied in the private sector, is going to impact quality of life? I think that's going to help sell a lot of this.
Well, there's sort of a high ground and then there's the specific ground. On the high ground, as I mentioned earlier, when we ask our contractors, our companies, to build these detectors, to build the spacecraft, the propulsion systems, the power systems, we're asking them to do things that no one has ever done before. And we push the engineers and the technicians and even the managers to do things that cause companies to be stronger. On the other hand, once we build these things, for instance, the ChemM instrument on the Mars Curiosity rover, those developments are quickly turned around into things that are commercialized and used here on planet Earth, whether it's to look for counterfeit drugs or new detectors for cameras that very quickly make it into cell phones, handheld devices for detecting explosives and chemical agencies, new detectors that are used in our defense industry, and the list goes on. Almost every one of our scientific instruments is relatively quickly through the development cycle mapped to something that is either commercialized or has commercial benefit.
I have one last question quickly, and that is in regard to the near-Earth objects. Is there any plans for a manned mission to any of those? My understanding is that there's some potential for a lot of benefit in terms of exploration of a near-Earth object.
So we have a mission in the Science Mission Directorate called OSIRIS-REx, which is a robotic mission to go out to a potentially hazardous asteroid. It's 500 meters across, grab some samples and bring it back to Earth, where scientists will analyze it. And also the administration has proposed, NASA has proposed the asteroid redirect mission, which is going to bring a near-Earth object into a lunar orbit, where the Orion spacecraft and SLS will then deliver astronauts to interrogate the asteroid.
I see my time has expired. I don't think that bill was acknowledging that, but thank you, Mr. Chairman.
Thank you, Mr. Palmer. The gentleman from Michigan, Mr. Molinar, is recognized.
Thank you, Mr. Chairman, and I also want to thank the panel for your presentation and just answering these questions. I want to go back. A number of people have brought up this topic of STEM education, the next generation, and how planetary science can really inspire. And what strikes me, and my history may not be 100% accurate, you guys would know better than I do, but You know, as I look through history, there was an issue of military competition or superiority with Sputnik, where, you know, we were in a race with the Soviet Union. There was the President Kennedy saying we wanted to land a man on the moon. There have been different commercial goals with space exploration. But it seems to me in every one of those cases, there was sort of these unifying goals that got, you know, NASA and the country sort of rallying behind something. And then, you know, if you watch a movie like October Sky, you see how students wanted to build rockets. And it really galvanized public support and private, you know, interest as well. If I had to ask each of you if there were 3 unifying goals right now when you think of space exploration, you know, I would think of things like, you know, military and defense applications, you know, commercial technologies, you know, origin of life questions, life beyond. Are there 3 that you can think of that really captivate sort of the mission that we're on today? If there were kind of unifying goals that everybody would say, yes, those are the goals, or are they all different? And that's one of the reasons it's challenging to communicate maybe the priorities for the next generation.
Well, let me start off, and again, I'll kind of take the high plane, and then we'll see where it goes. But what drives me as the head of science for NASA are really 3 questions. Where do we come from? You know, what is our origins? Where are we going? Where's the universe going, but also where are we going here on planet Earth? And then the final one, which, you know, for me is sort of the highest priority, but I don't want to pick favorites, is are we alone? You know, and I think, you know, that's one where people really, not everyone, but many, many people on planet Earth want to know, are we alone in the universe? And we are on the cusp of being able to answer that question technologically because of the investments we're making in space technology, both on the ground and in space.
Well, I'd speak to some other threads. In terms of the science, I think that there's a vast interest in understanding our origins, which we do not only through the planetary program, but through the astrophysics program, for example, as well, in NASA's Science Mission Directorate. Exploration, I think, is a very important theme. I think people in the public really are excited by exploration, as shown 2 weeks ago by the exploration of Pluto and the viral response that it got. That's a very important way that we can motivate and excite people about just what we as humans can achieve. And finally, I'd like to speak to tech careers. All of us are in tech careers as scientists or engineers or technologists. And I know I see this a lot in speaking about New Horizons, the other missions that I'm involved in. Young people are really envious of careers in the space program. And from my understanding, although space excites lots of kids to go into tech careers, about 90% or something in excess of 90% end up in other aspects of the tech economy, which I think is just fantastic, that we are the attractors to fuel the economy of the mid-21st century. And yet we don't need all those jobs to make the space program go, that it can go to fuel the internet and the biotech and other revolutions that we all want to see improve quality of life.
Yeah, if I could add to that for a moment, I think so. Both John and Alan spoke to the knowledge benefits that our space program provides, and that is clearly what is most relevant to the hearing today. Economic benefits are strong. Alan just alluded to some of those, but let's not leave out national security. Our ability to inspire people worldwide has international implications that are very helpful to this country. And there are really some very significant societal benefits. It's hard to go anywhere in our society today and not be impacted by something that came from the space program, whether it's the clothing that you're wearing while you're skiing or nutrients that are in about 80% of the baby formula that our infants in this country are taking as supplements. So, you know, those are a number of other reasons. If we have time, I'll speak to the "Are we alone?" question just for a moment. This is really a question that drives when I go out and talk with school kids. What really inspires them, really gets them interested.
And if we think about its relevance for science, we have just one example of biology on our planet. It all works kind of the same way, uses the same amino acids and uses the same storage for energy. And if we, by exploring a place like Europa or other icy moons or Mars, could find an example of a different kind of life, and on the outer planet satellites, that would have to be an independent origin of life, whereas at Mars there could be transfer between Earth and Mars that happened early in the solar system. It would be remarkable to see, is it similar to life on Earth, or is it completely different? Does it use different molecules? Does it have a different handedness of those molecules? It would really revolutionize the field of biology.
Thank you, Mr. Molinar. You all might be interested in knowing that we have a hearing scheduled in September on that subject, Are We Alone? So we will follow up. We've had hearings before. We're going to have another one in September. The gentleman from Illinois, Mr. Holtgren, is recognized for his questions.
Thank you, Chairman. Thank you all for being here. This is very important and actually exciting for us and important for us to be talking about these things. So I want to just thank you for your work. Thanks for being here today. I do especially want our kids to know that there is a future in science because by definition, these are smart kids that would be interested in this, and they will make the smart choice and avoid these fields if we are not supporting it. And so it is so important for us to support science and space and exploration. Dr. Grinsfeld, you said it best in your written testimony, so I'm just going to quote it again, and it doesn't get said enough, that space exploration is difficult, requiring our best and brightest engineers and scientists in order to succeed. And when we develop innovative probes to explore the solar system, we invent technologies which improve our lives here on planet Earth. I also think the same can be said about all the other, and I quote, big science projects that we're working on, be it at CERN or the North Pole or a mile underground at the Sanford Underground Research Facility trying to detect dark matter, which I had the pleasure of touring just a couple of weeks ago. But again, for me, a lot of this does go back to figuring out how we can get our kids to get into these fields. NASA does a lot of great work in the STEM fields, and frankly, I wish our other research agencies had the ability to get into the classroom more easily. If I were administrator, I'd probably be pushing for a few days paid leave if my scientists wanted to go and help kids to build robots or visit a science class. If nothing else, we should be doing everything we can to help our scientists volunteer. They do this because they love it, not to make a buck. Would ask each of you if maybe you could share with the committee as we're closing up this hearing, if there was a teacher or mentor or role model that convinced you that this is what you wanted to do, if you could kind of give a shout out to that teacher or mentor. And when was it that you actually realized that this would be your path? Were you a kid? Were you in college? Were you a postdoc? And what do you think is maybe the most important time for kids to get exposure to this work?
I'll go ahead and start. I really appreciate your comments. I have a belief that all children are born as scientists and engineers. We crawl around, we try and figure out how does the world work. In fact, we're genetically programmed to do that. And so it's up to parents, which are the largest demographic of decision makers in our country, to make good decisions on the education of our children. And I'm just very lucky that I had two parents that were very nurturing and interested in science and nature. But in the third grade, I was asked as part of my class, south side of Chicago, Hyde Park, Mrs. Loeb, first biography I ever had to write. And she started in the front row, and she started just assigning people for students to write about. So there was, Abraham Lincoln, George Washington, Babe Ruth. And she got to me, I was in the second row, and without missing a beat, she said Enrico Fermi, and then just continued on down the line. And my heart just sank. I thought, why didn't I get somebody famous? Well, Enrico Fermi, an American-Italian physicist who helped in the Manhattan Project, turns out, I met her years later and thanked her and gave her actually a patch that I flew on the space shuttle and met with the students and subsequently flew a patch that the students designed on another space shuttle from the south side of Chicago. But she said it was totally random. But Enrico Fermi, I grew up on the south side where Enrico Fermi taught, and so I got to meet people that he interacted with. I got to ride my bike to the first atomic pile, and I was just fascinated by it all, and I credit that with, becoming an astronaut and a scientist and being here to talk to you about it.
That's great. Any other?
Well, if we're taking this in order, I would say that I don't remember ever wanting to do anything else in my life except be in the space business. You might say that there's a fine line between being in the groove and maybe stuck in a rut. But I always wanted to do this, and I always drove to be able to do it. My parents supported me very strongly in that, and had many teachers along the way. And what I've noticed in raising my own children is that when they're interested in science and technology, oftentimes that they go through this mid-period somewhere in middle school and the early parts of high school where a lot of kids drop out of their interests in science and tech. And personally, my advice has always been to follow your heart, and the rest will probably work itself out. My own mentor that I'd like to mention is a little counterintuitive. It was much later in my life because I emerged from graduate school as an engineer and worked as an engineer in the space program, but had a bent towards science that was recognized by my laboratory director, Dr. Charles Barth, of the University of Colorado, and he kept slotting me into scientific positions, although an engineer, as project scientist for a satellite, project scientist for a sounding rocket, and he made me fall in love with science. So I went back to graduate school at age 30, and he believed in me, so it really made a difference.
Just a short
Our time goes by too fast, but yeah, if you can just maybe give a quick shout out to a teacher or mentor.
Right. I had a guidance counselor who was trying to push me into engineering, but I knew deep down inside I wanted to be a scientist, and I didn't listen to her.
Good for you.
Sure. Tom Kramer on Long Island might be out there watching this webcast as well, and inspired me in 6th grade. And as I mentioned in my testimony, Carl Sagan during my college years. And I want to point out the issue that when I taught elementary school science lab, there was such enthusiasm and excitement among the entire class, including the girls at that level. And we lose a lot of the girls when going to the junior high and high school levels, and I think that's something we continue to need to work on.
Yeah. If I could just quickly add, I grew up in Maryland, in Rockville, Maryland, and my father was an engineer at the Applied Physics Lab, where New Horizons was flown from. And that was, he certainly inspired me to, in an engineering direction. But when I was 11 years old, Viking landed on Mars. And I was fortunate enough to be able to go to the Goddard Space Flight Center to witness that landing. And there was a guy on TV, a TV screen, jumping up and down. He had long hair. He was wearing a very colorful shirt. He was some kind of engineer, and he was very proud of that moment of that first U.S. planetary lander. And I thought, boy, I want to be like him. And it turns out that guy was Gentry Lee at JPL, who I have since had the great fortune of getting to work with as a colleague. And he's still as energetic as he ever was.
Well, thank you, Chairman. Thanks for your indulgence. All of you, I think, certainly are providing some of that same inspiration and mentorship to young people today, and so I want to thank you for that. Quickly in closing, Dr. Grunsfeld, unfortunately, like you said, all of us are born engineers. I think I was unfortunately born a lawyer, and so I think that's a curse. But I wish I had your abilities, but I share in it and want to champion what you're doing. So thank you, Chairman, and I yield back.
Thank you, Mr. Holker. With that question, you all have made all your mentors proud.
Absolutely.
If you haven't surpassed them. And so that's nice to see. And with that objection, the gentlewoman from Maryland, Ms. Edwards, is recognized for an extra minute.
Just a minute. I had a question, but I really actually wanted to point out, and none of you did, there was a recent news report that said the New Horizons, on the New Horizons mission, there were 25% of the team that worked on New Horizons were women. And I think that that is something that we need to really celebrate. My recollection when the Curiosity rover landed, there was a team of women who were the team that developed one of the major instruments there. I think that we have the potential to inspire a new generation. And when I looked at that photo on NASA.gov, everybody go to it. That team of women right there in that photo, it gives me chills. Thank you very much, and I yield the balance of my time.
Thank you, Ms. Edwards. This has been a wonderful hearing. Thank you all for inspiring us, and we look forward to being in touch. And we are adjourned.